This playlist deals with some aspects of Eurocode 2 version 2023. Watch this channel for further selected topics. The video will deal with clause 11, detailing of reinforcement, part 1. The rules given in clause 11 apply to ripped and indented reinforcement, meshed and post-tensioning tendons. The ripped reinforcement looks like this picture. The intended reinforcement is a little bit like this. It means that the ribs are cut out of the steel bar, and the mesh, of course, looks a little bit like that. But what about plain rebars? In existing structures, you have a lot of plain rebars. So why is clause 11 not fit for plain rebars? What do we have to do to handle the plain rebars regarding the detailing? Or, for instance, coated rebars. What will happen with coated rebars? Because clause 11 is not valid for those two. The clear distance, CS, horizontal and vertical, between individual parallel bars should be not less than the value given in this formula. With CS, it's the clear distance horizontal and vertical, and the clear distance must be bigger than the maximum of the used diameter V. D upper plus 5. Note, it says D upper, not D max. D upper plus 5 millimeter or 20 millimeters. So in practice, when you use a clear distance of at least 40 millimeters in your constructions, you will comply in most cases with this formula. And then it's easy to use. You do not have to recalculate this all the time. Vmax is the, by definition, the declared value of the upper sheath size D of the coarsest fraction of aggregates actually used in the concrete, according to EN206. The upper, the definition of it is the largest value of the upper sheath size D, the same as above, in an aggregate for the coarsest fractions of aggregates in the concrete, which is the same as above, permitted by the specifications of the concrete according to EN206. So you see clearly the difference. D max is actually used maximum size, and D upper is the one which is the maximum permitted one. So this means that if the actually used D is smaller than the upper, which can be the case, bigger is not possible because that's not allowed, of course. But the actual used diameter can be smaller than the diameter allowed or permitted by the specifications of the concrete. Well, in this case, if the actual used D is smaller than the upper, you still have to use the permitted value for CS. So that's a common mistake. So it's not because you use the concrete with D max equal to 16 that you can plug in this formula 16. You must look at the environment, and you must decide from the environment, or you must decide from the conditions state put into the EN206 what is the permitted maximum core size aggregate. Now let's talk about bundles. A bundle of rebars is when two rebars are very close to each other, so there's no clear distance CS between them, when they are put very close to each other and they have at least 2 points of contact with each other. Each bar must have 2 points of contact. Then you can do that, but the amount of rebars must be smaller than 3, so you can use 2 or 3 bars. The clear distance between bundles of rebars must be at least equal to the equivalent diameter of the bundle. And the equivalent diameter of the bundle is equal to the square root of 4 over pi multiplied by the total area of or the total cross section of the reinforcement of the bundle. This is a slightly different definition than in the Eurocode version 2004. So I prefer to work with the following formula. The equivalent diameter is equal to the square root of the sum of the bar diameters squared, different bar diameters squared. But in most cases, in a bundle, all diameters are equal. So in most cases, this formula will lead to the equivalent diameter is the diameter of one bar of the bundle multiplied by the square root of the number of bars. So it means the square, when you have 3 bars, you have to multiply it by 1.7. And when you have 2 bars, you multiply it by 1.4. A bundle of bars can also have a number which is smaller than 4. So you can have 4 bars in one bundle, but that is only the case when you have a lapping or a lapped joint. For instance, in this drawing, you will see this is continuous two lapped of a lapped bar with 2 bars, or a bundle with 2 bars, and it's overlapping with another bundle of 2 bars. So in this lap length, you can have a maximum of 4 bundled bars. Otherwise, it's always should be smaller than 3. When there is compression, you can also use a maximum of 4 instead of 3. Now let's talk about the mandrel diameter. The mandrel diameter is a diameter like it's stated on this sketch, which is the radius of the bend. You have here a reinforcement bar with diameter phi, and you have a bend or an angle of alpha, which is defined positive as indicated here on the figure. The mandrel diameter is, or the minimum mandrel diameter, you cannot go lower than this. It's 4 times the diameter for diameter smaller than 16 and 7 times the diameter for diameters bigger than 16. The definition of CD, we will see that in the formulas we will have the factor CD, which is a concrete cover. It is stated in 11.4.2 paragraph 3. It is stated that is the minimum of half of the distance, clear distance between the rebars, as indicated in this figure, or it is Cx or Cy indicated here, which is the total concrete cover on the rebar itself, Cx, Cy in the 2 directions, or 3.75 times the diameter of the bar in question. So it's a minimum of those. That's the definition stated in this paragraph. Now, we will see that in the document, in the Eurocode version 2023, you have 3 definitions of CD. This was the first one. Then you have another one, which is stating CD is the minimum of the clear distance Cx from an edge parallel to the bend and half the clear space between bars CS according to figure 11.3c. So they refer to this figure. But the problem here is this CD is only defined for Cx and 0.5 CS, not for Cy and not for 3.75 feet. So that's a different definition. On figure 11.6, you have a new definition, which is stating that CD is the minimum of 0.5 CS, okay, Cx, Cy, okay, that we can see, and Cyb. So figure 11.6, Cyb is this. It's in fact a combination of Cx and Cy. But No harm done there. But again, it's different from the definitions in 11.4.2 part 3. Where is the 3.75 fee? So now, because of the missing 3.75 fee in the different formulas, we will take in what is following, we will take the first definition as the definition which is correct. So it means that for very small diameters, the 3.75 phi can be dominant. Formula 11.1 gives you the maximum allowable steel stress in the reinforcement to make sure that the concrete in the bend is not crushed. So it's for making sure that there is no concrete crushing. Of course, sigma SD should also be smaller than FYD. That's obvious. In this formula, you will see that you have sigma C conf D, the design value, which is given by this formula. In the code 2023, the sigma C conf of confinement, I think it's from confinement, and the design value of it, this value was directly plotted into formula 11.1, but it's more handy to separate those two values. K bend, it's a factor taking into account the angle of a bend or the angle of a hook, and alpha bend is in degrees. FCD, like we've seen in the first videos, the definition, but I just repeat it to make it easy that you can apply this formula with eta cc equal to this. FCK ref, I will use the proposed value of 40 megapascal, but this can change in the national application documents. And DDG is also defined. We talked about this in the previous videos. Now, at the minimum mandrel diameter, the allowable steel stress limited by FYD can now be plotted against the reinforcement diameter. Just to give you an idea what this formula means, formula 11.1, what it means. And we will do this exercise for two typical cases. The alpha bend equals to 90 degrees and 1 to 180 degrees. 90 degrees, it corresponds to stirrups. 180 degrees, it's a typical pin. We will also take the worst case, which is Dmax 32 millimeters. And CD, the factor CD, this depends on the environmental class. So you have a lot of combinations possible. But for this exercise, we will take 40 millimeters, which is equal to the C nominal plus the diameter of the stirrup. And we will take the minimum of the 40, like we have chosen, and 3.75 times the diameter. So for small diameters, then the 3.75 phi will be dominant. Just to enlighten or to show what the system is all about, I will take one case, which is a case for the concrete quality of 30 megapascal, the yield stress of yield strength of the reinforcement 500 megapascal, the angle of 90 degrees, a Dmax of 32, and CD the minimum of this. Well, now we can look at this graph. On the x-axis, it's the diameter used from 6 up to 32 millimeters. And the steel stress, the maximum of the maximum steel stress allowed to avoid crushing of the concrete is given on the y-axis in megapascal. This is the line, the limit for sigma SD for for a tensile for a yield strength of 500 megapascal. So this value is 500 divided by 1.15. It's 435 megapascal. That's the black line. So it means that everything above this line, it's okay, because the allowable stress to avoid crushing is bigger than the yield stress, or it's bigger than the design value of the yield stress. Everything below, it's not okay in the sense that you cannot use the stirrup, for instance, to its full capacity. And when we look at this specific point, then you will see for a bend of 90 degrees, the maximum allowable steel stress when it's smaller than 435 megapascal, in most cases, then the diameter must be smaller or equal to 12 millimeters. So this means alpha bend 90 is like a stirrup. You cannot use a stirrup with a diameter 14 to its full capacity, because the maximum is 370 or something like that. This is in the conditions that we use the minimum allowed mandrel diameter. You can now just visualize this in a table with different values. On the X axis, you will have the concrete quality. On the Y axis, the different diameters of the steel. And in the table gives you the sigma SD, the maximum allowable steel stress to avoid crushing of concrete. And you will see now for C30, this is our previous example. The graph on the previous slide is based on those values here. And you see again, as from diameter 12, it's okay, more or less. It's a little bit buff, but anyway. And for the diameter 14, you cannot go to the maximum load. The red zone in this table means that at a bend of 90 degrees, for instance for stirrups, the maximum allowable tensile stress is smaller than the 435 megapascal. So this is really annoying, because you will see now that a diameter 6 and 8 you cannot use to its full capacity. Only for a concrete quality C2025, you can use only diameter 6 and 8. For C30, you can only use 6 up till 12, and so on. Only for C90, you can use all diameters for stirrups. Now, once that we know the system, we can now make a total graph of different cases. On the x-axis, again, the diameter of the rebar, the y-axis, the permissible stress in the reinforcement. And we've put on this graph the maximum values for BE500, 450, and so on, up till BE700. So up till the yield strength of 700. Of course, this is 700 divided by 1.15 and so on. So for 500, you will have 435. The different lines that you can see is sigma SD in function of the diameter, but with different concrete qualities. So the concrete quality starts with 12, then 16, then 20, and so on. The top is 90 megapascal. So the concrete quality increases in this direction. We see that for the highest possible concrete grade and the highest possible yield strength, that the maximum diameter of the stirrup is 14 millimeters. We use it in full capacity, of course, with the minimum mandrel diameter. When I say the highest possible concrete, in fact, you can still have concrete C100, but it's not on this graph. When we look at the yield strength of 500 megapascal or FYD 435, we have seen that for C30, you have a maximum diameter of 12 for the stirrup, and for C20, 25, you have a maximum diameter of 8 millimeters. So at minimum mandrel diameter for the full capacity of the steel cannot be always used. So at the minimum mandrel diameter, the full capacity of the steel cannot be always used. You can now take the same graph as in previous slide, but we will hide the values which are not going to the full capacity of the steel. And then we look at this line of 435 megapascal. And then when it crosses the concrete quality, you have a maximum diameter of stirrup that you can use in full capacity. And I've put this in a table by using this graph, of course. And then you will see again for C30, the maximum diameter is 12, or for C50, the maximum diameter of stirrup is 20 to be used to its full capacity. Now we will look at a bend, an angle of bend of 180 degrees instead of 90. All other parameters stay the same. And you will see in this case, and this is again the line of 435 megapascal, that all diameters fall below the limit of 435 megapascal. So it means that not the stirrups, because it's under 80 degrees, that the pins cannot be used to their full capacity when using the minimum mandrel diameter. So again, we can visualize it in a table, and you see again that the red zone, it's at the bend of 180 degrees. The maximum allowable tensile stress is smaller than 435 megapascal, which is a complete range. Now we can look at all cases again for the different concrete qualities, and the concrete quality goes up from bottom to top. And you can notice immediately that in most cases, you cannot use a pin to its full capacity. Even for high strength concrete of C90, the maximum allowable pin diameter is less than 14. It's 12, in fact, and only a diameter 12 and smaller you can use to its full capacity. Also, you need at least, the blue line is C40, you need at least C40 to allow full capacity of a pin, but then with a diameter smaller or equal to 6. So this is quite disturbing, but we will see in the next video that we can do something about it.